All right, my friends, now that I'm done fumbling around. So, yeah, you see we have our Thanksgiving presentation on this. And it was funny, too. My fourth hour, somebody said, I never thought about this before. Somebody looked at the turkey and said, well, the turkey is going to increase in entropy, which is very morbid if you remember what the definition of entropy is. But that's kind of the purpose of a Thanksgiving turkey, is to increase in entropy for all of our benefit. Yeah, I'm going to move on from there. That was recorded, but that will not go on YouTube. So, chapter 6 is called thermochemistry, and then chapter 17 is thermodynamics. Aren't those two the same thing? Well, they must not be, since they're 11 chapters apart in the book. The reason that they are separated like that is because thermodynamics, at the end of 17, it starts to connect the thermochem with equilibrium. And since equilibrium shows up in chapters 13 through 16, there's 4 full chapters of equilibrium. Man, we start equilibrium around Christmas time. We'll go through into March with equilibrium. It's a lot, man, that's a big, big part of this class. Oh, is that bad? Yeah, it's a lot. Yeah. So, and that's just that's a big part of chemistry, and that's about all there is to it. Now, the difference between thermochemistry and thermodynamics. Thermochem is all about delta H. It's about heat flow. Thermodynamics, the term dynamic in there means changing. Thermodynamics incorporates all of the energy flowing in or out of the reaction, which includes another form of energy, or another expression, I should say, of energy in a reaction. You remember what that is? There's enthalpy, delta H, and then what other term? Entropy. Yeah, as I mentioned about the turkey, there's entropy, which I think, I don't have that on the next slide, but we'll see entropy here in a moment. The first thing that we'll see about thermodynamics is just a few definitions. The first one is the term spontaneous. Once you hear the term spontaneous in this class, which is now, we will come back to that. That will be a recurring thing that happens all throughout the rest of the year. We have to know whether reactions are going to be spontaneous. Just as an example. So you have the definition. A spontaneous reaction is a reaction that is going to happen under the current set of conditions. It's going to happen. It doesn't need any help. You don't have to do anything with it. It's just going to happen. I should be careful when I say that. A lot of times a spontaneous reaction does need a boost. It needs what we call the activation energy. Once it has that little boost of energy, then it'll just go on and on and on, and it will happen. But yeah, there are some spontaneous reactions that will need a boost. The word spontaneous, when I hear spontaneous, and not in a chemistry sense, a lot of times people are described as spontaneous. You know, you sometimes hear a girl talking about how much she likes a guy because he's spontaneous. And what does that mean? It means that the guy he's just a doer. He doesn't have to sit and think and plan things and just go on and do things. And sometimes, you know, that's related to a sense of adventure, even. And so, you know, it's a personality thing. But you'll hear guys sometimes, and I see fingers being pointed. Rashid maybe is a spontaneous kind of a guy, which is great. Yeah? And I mean, it's not a benefit or a fault even if you're not. It's just one of those things that makes us all unique. Now, with regard to reactions, what causes a reaction to be spontaneous? How do we know if one will be spontaneous? We care about whether reactions will be spontaneous. A couple of examples. Batteries, like AA batteries, AAA batteries, camera batteries, all the batteries that we have chemicals inside of them in which there is a chemical reaction that's going on. That reaction has to be spontaneous, otherwise we're not going to get any voltage out of the battery. So batteries depend on a spontaneous reaction happening inside of them. People that use iron care that iron rusting is a spontaneous process too. And there's a lot of effort that gets put into slowing that process down, preventing iron from contacting the air so that it can't rust. And if you get a chip in the paint, you could have a rust spot showing up, and then it will just happen that the rust will kind of permeate in even underneath the paint sometimes. So spontaneous reactions are a really important consideration. A lot of times people that are engineers need to know whether a reaction will be spontaneous, especially chemical engineers. Material science engineers do too. All right, well, originally, back when chemistry was a baby, people in chemistry thought that all it took for a reaction to be spontaneous was the release of heat. They thought all exothermic reactions were spontaneous because that's a chance for matter to release some of its stored energy. After that theory, though, was considered and tested, people found out, no, that's not quite right. There are some endothermic reactions that are spontaneous. I have a picture of one. It's a really sad picture. I don't even like to look at it, really. Look at that. Isn't that a sad picture? This is an endothermic process. Me too. I don't like it. The ice cream is melting because it's taking in heat. That's the only way it can melt. And that is the opposite of exothermic. So we had to figure out, okay, this is an endothermic process that is spontaneous. Nobody is doing anything to cause the ice cream to melt. It's just happening. So there must be something more than just delta H that dictates whether a reaction is going to be spontaneous or not. Delta H contributes to it. That's where we get this other expression of heat, the entropy. All right, so entropy is defined. In chemistry, we define entropy as what? Like a disorder. That's all we always say for entropy, is it's a form of disorder. This is not the pure definition of it. This is a general chemistry attempt at defining and wrapping our brain around entropy. Entropy is actually much more complicated than that. But for now, it just suits us very well to think of entropy as disorder. When somebody studies chemistry long enough, they find that chemistry and physics really start to become the same thing. And entropy is really more of a physics concept that has a physics definition. I'll tell you what the definition is in the physics context in a couple of minutes. So now I think you had done enough with entropy in Chem 1 to know a few things about it. You know that it was disorder. And there's three major things that will tend to increase entropy. I think you've learned about these too. Entropy increases when, first of all, a gas is produced. Gas particles are much more free to move around than solids and liquids, the particles of those. So, yeah, the production of a gas always increases molecular motion and therefore increases entropy. And nature tends to increase its entropy. When you leave nature to just do its own thing, it becomes more messy or more disordered. For instance, if I take spaghetti noodles out of the package and I just throw them up into the air, how likely is it that they'll fall down on the floor in a nice, neat, organized pile? It's not very likely. They'll be all over the place. I've been picking up spaghetti for a long time. That's the way nature works. Nature tends to become more messy. The leaves are falling off the trees. is it possible that they could all fall into a nice, neat pile? So I could just walk up to the pile and bag them up?